Okay, so our first goal for today will be to study a relation between GNS representations and cyclic representations of C-star algebras. So roughly, we're going to show that these objects, I mean GNS representations and cyclic representations, are essentially equivalent. Okay, so suppose that we have a C-star algebra A. And suppose that f is a positive linear function on A. And as usual, we denote by pi f the respective GNS representation of A. GNS representation associated to the functional f. Let's recall some notation. So we have a canonical map, lambda f, from A to the Hilbert space HF, which takes each element A to the respective element in the quotient, A plus NF. So we recall that if we quotient out a suitable subspace of A, then the resulting quotient becomes an inner product space, and HF is just the completion of this inner product space. The representation pi f acts on the image of this map lambda by the following formula. So this is just the left multiplication modulo the subspace MF. And the inner product of vectors in the image of lambda, the inner product is given by the following formula. To motivate our further constructions, let's first of all briefly discuss the unital case. So we start with the following simple observation. So let's suppose that our algebra A is unital. And let's denote by xf the following vector in our Hilbert space. This is the image of the identity. So what can we say about this vector? So when we act by our representation on this vector, what we get is just lambda A. Well, indeed, this is a special case. This is a special case of this formula. So if we substitute the identity for B here, then we get this. And now, since the image of lambda is dense in the space HF, this implies that XF is a cyclic vector for the representation pi f. So we see that in this case, in the unital case, the GNS representation is cyclic. And also, the functional f can be reconstructed from this cyclic vector by the following formula. Well, indeed, this formula is a special case of this one. So if we substitute the identity for B here, then we get this. Okay, so our first goal will be to extend this observation to the non-unital case. So we'll show that each GNS representation is cyclic. And our second goal will be to prove the converse statement, that each cyclic representation is unitarily equivalent to a suitable GNS representation. So let's start with the following lemma. Let's take an approximate identity in our sister algebra A. Let E lambda be an approximate identity in A. So as usual, we follow our standard convention that an approximate identity is positive, is bounded by 1, and is monotone. I claim that, first of all, E lambda squared is also an approximate identity in A. And second, if we send this approximate identity to the respective Hilbert space, lambda f plus of E lambda, then this goes to the canonical image of the identity in the unitization of A. So this converges in HF plus. Oh, by the way, maybe it's appropriate to recall what F plus is. So F plus is the canonical extension of F. So F was a positive functional on A, and we know that each positive functional has a canonical extension to the unitization. So let me recall how this F plus is constructed. So F plus is defined on A plus by the following formula. This is f of A plus mu multiplied by the norm of A. This is the canonical extension of F to the unitization. So we know that F plus is also positive. Also, we know that the norm of F plus is F plus evaluated at the identity. In fact, this equality is equivalent to the positivity of F plus. And if we substitute the identity of A plus in the above formula, then we get that this is just the norm of F. So the norm of F plus is the same as the norm of F. So this is the canonical extension of F to the unitization. So the second part of our lemma shows that, of course, E lambda doesn't converge to the identity unless A is unitary. But after we pass to the Hilbert space for our generic representation, then the image of E lambda converges to the image of the identity. Okay, let's now prove the lemma. The first part is an easy application of the triangle inequality. So if we calculate the distance between A and E lambda squared, then this can be estimated as follows: A minus AE lambda plus AE lambda minus AE lambda squared, which can be written as follows. So this is immediate from triangle inequality. But now, since our approximate identity is bounded by 1, this can be estimated as 2 multiplied by the norm of A minus A lambda. And this goes to 0. And that's it. So this shows that E lambda squared is the right approximate identity. And by taking the joints, we conclude that it is also left approximate identity. Okay. And now to prove the second part, we again calculate this explicitly. So we calculate the distance between these two elements in HF plus. Lambda F plus of 1 minus E lambda. So for convenience, we'll take the square of the norm here. So the square of the norm is the inner product of this element by itself. And the inner product is given by this formula. And so this inner product of 1 minus E lambda by itself is nothing but F applied to 1 minus E lambda squared. So here I use the fact that this element is self-adjoint. But what is this? So this is F plus because we work in the unitization. So this F plus applied to the identity minus 2F of E lambda. Here I use the fact that F plus extends F plus F of E lambda squared. So now what can we say about this expression? Well, first of all, the first summoned is just the norm of F. It's just the norm of F. Let's now recall that the positivity of F is equivalent to the fact that F of E lambda converges to the norm of F. So this converges to the norm of F. But we already know that E lambda squared is also an approximate identity. So this number also converges, this net also converges to the norm of F. So after we take the limit, we get the norm of F minus 2 multiplied by the norm of F plus the norm of F. That is, the result is 0. So this converges to 0. Okay, and so this means precisely that E lambda, the image of E lambda, converges to the image of the identity. Okay, now by using this lemma, we get the following theorem. I claim that there exists a unique unitary isomorphism U between HF and HF plus. Moreover, this is not just a unitary isomorphism of Hilbert spaces, but it's a unitary isomorphism of A modules. So the A module structure on HF is clear because we have the GNS representation. Also, HF plus is a module over the unitization. But since A is a subalgebra in A plus, so HF plus also becomes an A module. So it's a unitary isomorphism of A modules such that U composed with U applied to lambda f of A is lambda f plus of A for all A in our algebra. Okay, so to prove this theorem, we first define U on the dense subspace in HF, namely on the quotient of A modulo and F. So we define map U0 from HF0 to HF plus 0. So these are the uncompleted versions of HF and HF plus. So we define it by the following formula. It takes A plus and F, that is lambda f of A, to A plus and F plus. So clearly this is well defined. And moreover, it's clear from the construction that U0 is an A module morphism. Because A acts as left multiplication. Also, it's clear from the construction that U0 is unitary. That is, it preserves the inner product. This is also clear because the inner product on HF0 is defined in terms of F, and on HF0 plus, it is defined in terms of F plus. but F plus extends F. So U0 preserves the inner product. Okay, so U0 is unitary. And also, if we now apply our lemma, we conclude that the canonical image of the identity of the unitization sits in the closure of the image of U0. So this follows from the second part of our lemma. So look here, this is in the image of U0, and this converges to lambda f of the identity. So this element sits in the image of U0. And now let's observe that elements of this form, A plus and F plus, where A rounds over A, together with this element, so they span a dense subspace in HF plus. So this implies that the image of U0 is dense in HF plus 0. Okay, so we have a unitary isomorphism between HF0 and the dense submodule and in HF plus 0, and we can extend by continuity to the completion. So extending U0 by continuity gives us a unitary isomorphism. U0 uniquely extends to unitary isomorphism U between HF and HF plus. And this is a unitary isomorphism of A modules. And this completes the proof. Okay. A short remark, which gives us an equivalent way of thinking about this isomorphism. So we have the following commutative diagram. Let's draw the following picture. So here we have the GNS representation F of A. A is, of course, a subalgebra in its unitization. And we also have the respective GNS representation pi F plus of A plus. And now the isomorphism U, the unitary isomorphism U, implements an isometric star isomorphism between these two algebras, which is usually denoted like this, AD of U, the joint star isomorphism, given by the following formula. It takes each operator T on HF to the following operator on HF plus. So this is an isometric star isomorphism. And clearly this diagram is commutative. In fact, the commutativity of this diagram is equivalent to the fact that U is not just a unitary operator, but is also a unitary isomorphism of A modules. So the commutativity of this diagram means that U is an A module isomorphism. So it intertwines pi F with pi F plus. Okay. Okay, now we are ready to show that all GNS representations are cyclic. So we have the following theorem. First of all, let's adopt the following convention. So from now on, we will identify HF with HF plus by means of U, pi F of A with pi f plus of a by means of this AD of u, and lambda f of a with lambda f plus of a for all elements in our algebra. Again, we identify them by means of u, of the isomorphism u. Okay, so now we have the following theorem. We define an element xf in hf to be the image of the identity in the unitization array. So here I identify hf and hf plus. I claim that xf is a cyclic vector for the GNS representation for pi f. Also, if we apply pi f of a to this vector, then we get lambda f of a. And this vector xf is uniquely determined by the following formula. F of a is the inner product of lambda f of a and xf. So in some sense, this vector is a canonical cyclic vector for the GNS representation. So now if we come back to the unital case, so this is the unital case, we see that so what we've just constructed is oh sorry, the unital case is here. So this is the unital case. So if we now come back to the unital case, then we see that what we've just constructed is a generalization of this observation to the general case, to the case of an arbitrary C-star algebra, not necessarily unital. The proof is very easy, just an explicit calculation. Let's apply pi f of a to xf. So we identify pi f of a with pi f plus of a. Xf is by construction lambda f plus of the identity. And by the property of GNS representation, this is just pi f plus applied to the product, but the product is just a. So this is just pi f of a. Oh, sorry, this is, of course, not pi f, by lambda f of a. So this proves this formula, and also this implies that our vector is cyclic, because we already know that the image of lambda is dense in nature. So in particular, this formula shows that xf is cyclic. Okay, now we have to show the second formula. Again, we calculate the inner product of lambda f a and xf. We replace lambda f of a by lambda f plus of a, and xf by lambda f plus of the identity. And again, this is nothing but f plus of a, that is f of a. So we see that xf satisfies this condition. And finally, the uniqueness of such a vector is clear because elements of this form, lambda f of a, span a dense subspace in HF. So the uniqueness follows from the density of the image of lambda in HF. Okay, so this completes the proof. So we see that each GNS representation is cyclic. And now let's show that the converse is also true. So we have the following result. Suppose that we have a cyclic star representation of A on a Hilbert space H. Cyclic star representation. And let's choose a cyclic vector, X. Let's now define a functional. We define a functional f of A by the following formula. This is the inner product of pi away x and x. The formula is very reasonable because if you want to prove something, a statement which is converse to the previous theorem. So if we'll now look here, so we can substitute instead of lambda f of a, we can write here pi away x. So f of a will be the inner product of pi away x by x. So this shows that if we want to prove the converse statement, then the only way of defining f is to define it by this formula. And this is positive. Some time ago, we discussed that such functionals are positive. I claim that there exists a unique unitary isomorphism U between H and HF, a unique unitary isomorphism of A modules such that U takes X to the canonical cyclic vector XF, which was constructed in the previous theorem. So in particular, we see that each cyclic representation is isomorphic, is unitarily isomorphic to a GNS representation. To prove this result, we recall the abstract characterization of GNS representations. And we construct a map lambda from A to H by the following formula. Lambda A is pi away applied to the cyclic vector X. So what can we say about this map? Well, first of all, since X is a cyclic vector, we see that the image of lambda is dense in H. Second, if we calculate the inner product of lambda A and lambda B, so this will be the inner product of pi away x and pi of bx, and we can move now pi of b from right to left, and we get pi of b star pi of a x, and we take the inner product with x. But pi is a star representation, and so this implies that this is nothing but our functional f applied to b star a. Okay, and finally, if we act by the operator pi away on the vector lambda of b, again by construction, by this formula, what we get is pi of a pi of bx, so that is lambda of ab. So these equalities imply that the triple consisting of h, pi, and lambda is an abstract GNS representation. Abstract GNS representation associated to F. So let's recall that an abstract GNS representation is such a triple consisting of a Hilbert space H, a representation pi of A on H, and the map lambda from A to H, such that lambda satisfies the following three conditions. So the image is dense, the inner product is given by this formula, and the action is given by this formula. And we proved some time ago that such a representation is essentially unique in the sense that there exists a unitary isomorphism. U from H to HF, a unitary isomorphism of A modules, such that U composed with lambda gives us lambda F. So to complete the proof, we have to show that U takes the cyclic vector X to the cyclic vector XF. Okay, let's write explicitly the condition that U is an A module homomorphism. So we have the following formula. This pi f of A U of X, of course. And we choose an approximate identity. So let E lambda be an approximate identity in A. Okay, so we know that P of E lambda X goes to X. This is true for any non-degenerate representation, and this was proved at the previous lecture. So after we substitute E lambda here in this formula, what we get is so the left-hand side converges to U of X. Oh, this is true, but this is so I want to get XF in the image. Why is it XF? Uh, okay. This is true, but this is also true in HF. So we have this formula. Maybe let's denote this element by a different letter. So this is true for each y. So now if we substitute here, so power away x is lambda away. U composed with lambda is lambda f. So the left-hand side will be lambda f plus of E lambda. And the right-hand side will be pi f of E lambda applied to U of x. And after we take the limit here, we know that lambda f plus of E lambda goes to xf. This is just a construction of xf. And pi f of E lambda applied to U of x goes to U of x. And that's it. So U takes x to xf. Of course, the uniqueness is clear. The uniqueness of such an isomorphism U is clear because x is a cyclic vector. So this condition determines U uniquely. Okay, so this completes the proof. So we see that each each cyclic representation is unitarily equivalent to a GMS representation. In fact, combining our results, now we get the following picture. This is a simple exercise for you, which easily follows from our results. So we get a bijection between the set of all positive functions on A and the set of unitary isomorphism classes of triples H, pi, and X, where pi is a cyclic star representation of A on H. So H is a Hilbert space, pi is a cyclic representation, and little x is a cyclic vector for pi. It's very easy to define, to introduce the notion of unitary isomorphism between such triples. It's just a unitary isomorphism of representations which respects the cyclic vectors. And it follows from our result that we get a bijection between positive functionals and unitary isomorphism classes of such triples. Okay, that's all what I wanted to tell you about GNS representations. And our next goal will be just to discuss tensor products of C-star algebras. Our goal will be to make the tensor, roughly our goal will be to make the tensor product of two C-star algebras into a C-star algebra. And of course, all tensor products here are taken over the field of complex numbers. our strategy will be as follows. So the first step will be to define the multiplication on the tensor product. And of course, this is very easy. The second step will be to define an involution on the tensor product. This is also easy, but this requires a bit of mathematical culture, because the involution is not a linear operator, but is an anti-linear operator. The next step will be to define a C-star norm on the tensor product. That is a norm which satisfies the C-star axiom. And this is quite non-trivial. We will see that in general, there are at least two different ways, different and non-equivalent ways of doing this. And finally, in general, there is no reason for the tensor product to be complete with respect to this C-star norm. And usually it is not complete. So the final step is to take the completion of the tensor product with respect to this C-star norm. Okay, so this is our program, this is our strategy. So let's start with the easy part of this program. So we have the following simple proposition. Suppose that A and B are two algebras. I claim that their tensor product, A tensor B, is also an algebra with respect to the multiplication uniquely determined by the following formula. So the product of two elementary tensors, A1, B1, and A2, B2, is the elementary tensor A1, A2, B1, B2. The proof is very easy. We just, as a first step, we linearize the product, the multiplication in A. So the multiplication is a bilinear map. So we can factorize it through the tensor product and get a linear map mu A from tensor product to A. And now to define the multiplication on the tensor product. So we want to construct a linear map from the tensor product of A tensor B by itself to A tensor B. Well, what we do, we just interchange these two factors by using the elementary properties of the tensor product. We get A tensor A, tensor B, tensor B, and then we just apply mu A tensor mu B, and we are now in the tensor product of A and B. So we get a linear map from here to here, or equivalently a bilinear operation on the tensor product, which clearly satisfies this condition. The associativity is a simple exercise which is immediate from this formula. Okay, so the tensor product of two algebras is also an algebra. Our next goal is to define an involution of the tensor product of two star algebras. This is easy, but this is not entirely trivial because the involution is an anti-linear map. And to work with anti-linear maps, it will be convenient to introduce a simple construction, which is not usually discussed in linear algebra courses. Namely, we'll define the conjugate space of a vector space over the complex numbers. So we give the following definition. Suppose that E is a vector space over the complex numbers. We define the conjugate space of E is to be the vector space EC, defined as follows. First of all, as an abelian group, this space is identical to E. So the underlying abelian group is the same. But the multiplication by complex numbers is different. So lambda x in the space EC is the same as lambda bar x in E. So first we take the complex conjugation, and then we apply the action of lambda on x in E. It's clear that the result will be vector space. To work with the space, let's introduce some more notation. For each element x in E, we denote by xc the same element x considered as an element of the conjugate space. As an element of EC. Then the above formula for the action of the complex numbers can be written as follows. Lambda xc is lambda bar xc for all complex numbers lambda and x in E. In other words, the identity map from E to EC, which takes each x to xc, is antilinear. So this is the complex conjugate space. It looks similar to E, but in fact, there is no canonical isomorphism between E and EC. Of course, they are isomorphic because, well, the algebraic dimensions are the same, but there is no canonical isomorphism. So the only canonical bijection, which is given by this formula, is not linear, is antilinear. Okay, let's look at some simple properties of this construction. So we have the following proposition. First of all, the space of linear operators from the conjugate space EC to another vector space F is the same as the space of antilinear maps from E to F. And this is the same as the space of linear operators from E to the conjugate of F. Second, we have a similar result about bilinear maps. So the space of all bilinear maps between, say, E1, C times E2C to F is the same as the space of all bilinear maps from E1 cross E2 to the conjugate of F. And this is the same as the set of all anti-bilinear maps from the product E1 cross E2 to F. And finally, part 3, I claim that there is a natural vector space isomorphism between the tensor product of two conjugate spaces, E1C and E2C, and the conjugate of their tensor product. And this isomorphism is uniquely determined by the following formula. It takes each element of the tensor of the following form to x1, x2 conjugate. Okay, in fact, the only statement which is not probably entirely trivial is part 3. Parts 1 and 2 are clear from the construction of the conjugate space. So let's prove part 3. Well, to construct such an isomorphism between these two spaces, it suffices to show that we have the following natural isomorphism. It suffices to construct a natural isomorphism between the space of linear operators from the first space, namely the tensor product of two conjugate spaces, and F, and the space of linear operators from the second space, that is the conjugate of the tensor product, to F, where F is an arbitrary vector space. Here I'm using the standard Dionnet dilemma from category theory, which states that, in particular, it implies that two objects are isomorphic if and only if the respective Hom functors are isomorphic. Okay, so this construction is very easy. Namely, if we start with the left-hand side, so by the universal property of the tensor product, we can write it as follows. This is naturally isomorphic to the space of all bilinear maps from E1C cross E2C to F. Now using the second part, by using this formula, we can replace this by the space of all bilinear maps from E1 cross E2 to the complex conjugate of F, Now, by the universal property of the tensor product, this is nothing but the space of linear operators from the tensor product of E1 tensor E2 to FC. And finally, we use the first part of our proposition, namely this identifications, and we conclude that this is the space of linear operators from complex conjugate of the tensor product to F. And this is exactly what we wanted to construct. So we get this natural isomorphism. Okay, let's now come back to algebras. We have the following simple proposition. Suppose that A and B are star algebras. I claim that their tensor product, A tensor B, is also a star algebra with respect to the involution, uniquely determined by the following formula. So you would take an elementary tensor, A tensor B, and take the star, then this will be A star tensor B star. Okay, well, the uniqueness is clear because each element is a sum of elementary tensors. So we have to show the existence of this involution. And to do this, we use complex conjugate spaces. So the involution on A, let's denote it by IA, is an antilinear map, but it becomes a linear map from A to the conjugate space. This is a linear map. Now, to define the involution of the tensor product, we take the tensor product of A and B. We take the tensor product of IA and IB. IA tensor IB. This will be a linear map to the tensor product of conjugate spaces. But we already know that this is isomorphic. This is canonical isomorphic to the complex conjugate of A tensor B. So we get a linear map from here to here, or equivalently an antilinear map from A tensor B to itself, which clearly satisfies this condition. Now it's very easy to show that this map is indeed an involution. It's a simple exercise that all axioms of the involution are satisfied. So the tensor product of two star algebras becomes a star algebra. Okay. Our next goal will be to construct a C-star norm on the tensor product. So as I said before, this is not trivial, but possible. First of all, let me say a few words about C-star norms. So we give the following definition. Suppose that A is a star algebra. And suppose that we have a norm on A. We say that this norm is a C-star norm. The C-star norm, if it satisfies the following axioms. First of all, it is submultiplicative. Second, the involution is isometric. And finally, the norm satisfies the C-star axiom. So this holds for all A and B in our algebra. And a star algebra equipped with a C-star norm is called a pre-sister algebra. So the only difference between pre-sister algebras and sister algebras is that a pre-sister algebra is not assumed to be complete. However, it's easy to observe. So let's do this. Let's observe that the completion of a pre-sister algebra is a sister algebra. Okay. Let's now recall that some time ago, we proved that if we have a star algebra, which has a norm, making it into a sister algebra, then this norm is unique. And in fact, this norm is given by an explicit formula. The norm of A is the square root of the spectral radius of A star A. We will need a slightly more general result, namely the following proposition. Suppose that A is a star algebra, and suppose that we have two C-star norms. Let's denote them as follows. Two C-star norms on A. And we assume that A is complete with respect to one of them. Suppose that A is complete with respect to the first norm. I claim that these norms are equal to each other. So the difference between this proposition and our earlier result is that we assume the completeness with respect to one of the norms, but not with respect to the second one. So this is slightly more general than our earlier result, where we assume the completeness with respect to both of them. Well, anyway, the proof is very easy. So let's take the completion of A with respect to the second norm. Let A1 denote the completion of A with respect to the second norm. And let's look at the inclusion map J of A into A1. So what can you say about this map? This is, of course, this is injective. And this is an injective star homomorphism. Between C-star algebras. So A is equipped with the first norm, and A1 is equipped with the second norm. And we know that an injective star homomorphism between C-star algebras is isometric. J is isometric. And that's it. So this means that the norms are identical. Okay, it's essential that if we drop the completeness assumption here, I mean, if we drop this assumption, then the result fails. So in general, if we have a star algebra, then there can be many different C-star norms on this algebra. And this fact leads to many complications in the theory of tensor products of C-star algebras. But in fact, these complications make the theory of tensor products of C-star algebras very interesting and rich. Okay, now as an application of this proposition, let's define a sister norm on the tensor product of a sister algebra by the matrix algebra. So we introduce some notation. Suppose that A is an algebra, an arbitrary algebra, and we denote by M and A the algebra of all square n by n matrices with entries in A. Well, clearly this is an algebra. And if we denote by Mn the algebra of complex matrices, of complex n by n matrices, then it's easy to see that we have an algebra isomorphism between the tensor product of Mn and A and the algebra Mn of A. So explicitly, this isomorphism is given by the following formula. If alpha ij is a complex matrix and little a is an element in A, then this elementary tensor goes to the A valued matrix alpha ij. This is an algebra isomorphism. Okay, we now have the following result proposition. Suppose that A is a sister algebra. Then there is a unique sister norm on the tensor product of Mn tensor A. And moreover, this norm makes tensor product, makes the tensor product Mn tensor A into a sister algebra. To prove this result, we choose a faithful star representation of A on a Hilbert space. That's denoted by pi. So the result is very strong. We use the second Gelfand-Dirac theorem. And it seems that there is no other way of proving this proposition. The proposition looks very natural and simple, but in fact, this is not so easy. And it involves the Gelfand-Dirac theorem. Okay, so we choose a faithful star representation of A on a Hilbert space, and we do the following. So we take the tensor product of M and A, and we send it to the tensor product of Mn and BOH. So this error is the tensor product of the identity map of Mn and pi. So this is an injective star homomorphism. From this algebra to this algebra. But what is this? By the above remark, this is isomorphic to the algebra of n by n matrices with entries in BOH. But this is nothing but the algebra of bounded operators on h to the power n, that is, on the Hilbert direct sum of n copies of h. And this is a C-star algebra. So we see that our map is a faithful representation of the standard product on h to the power n. Well, now it's very easy to define a norm. We define a norm on the tensor product as the norm inherited from b of h to the power n. Well, since our error is injective, we'll conclude that this is a C-star norm. Because B of Hn is a C-star algebra. Well, why is it complete? It's a simple exercise to show that the image of our homomorphism, one tensor pi, consists of those operators U on Hn, such that each matrix entry, so after we identify U with the respective matrix of operators on H, so each entry Uij belongs to the image of pi for each I and j. This is immediate from the construction of our homomorphism. It's a simple exercise to show that this is closed in B of Hn. This is an exercise. So this implies that the tensor product of Mn and A is complete. So this is a C-star algebra. And finally, the uniqueness of such a norm is immediate from our previous proposition. So we have constructed a C-star norm on our algebra, which is complete. So it makes it into a C-star algebra. And this implies that this is the only C-star norm on our tensor product. So the uniqueness follows from the previous result. Okay. Okay, so that's all for today. At the next lecture, we extend this construction to arbitrary C-star algebras. So we'll use the second defined Naimark theorem to construct a C-star norm on the tensor product of two arbitrary C-star algebras. And this will give us the so-called minimal or spatial C-star tensor product. Okay, thank you.